I want you to think back to the last time you watched a candle burn, something so common, but the flame on that candle danced around and it was consuming the wax, turning it into something totally different, right? But what's really happening down there at the molecular level, when you peel back the layers of the onion to really look at something that seems simple and try to really understand it? What mysterious process or force allows matter, which is all around us, to transform from one thing into another? And why can some materials combine to create entirely new substances while others just sit there completely inert and really doing nothing at all? Now, these transformations that we see all around us, they're not magic. At one time in the past, they sort of were considered to be magic, but we know they're not magic. They're chemical reactions. And today, what I'd really like to do is to discuss and talk about exactly what is a chemical reaction. Don't just say the word. I want us to all really understand what they are and how they differ from nuclear reactions, and how almost everything that changes around you in everyday life involves a chemical reaction in some way, shape, or form. Now, before we get into the nitty-gritty details of all this stuff, let's take a moment and look around us and really observe. Chemical reactions are happening literally everywhere around you in every moment of the day. That apple that you see on the counter turning brown after you cut it, that's a chemical reaction between compounds in the apple and the oxygen in the air. The rust that's forming on your bike chain changes color, changes texture. Well, that's another chemical reaction with oxygen. You eat something, it goes into your stomach, so your stomach breaking down breakfast, well, that's another chemical reaction. We're going to talk about that one a little bit more in a minute. What about that satisfying sizzle? When you're cooking dinner in a pan and it begins to sizzle, that's actually a chemical reaction that has a name. It's called the Maillard reaction. Even the process of photosynthesis, which literally keeps this planet running, generating energy in all of the plants, is a complex chain of chemical reactions, one after another, happening right in your backyard in every blade of grass. And the process where your body breaks down food and extracts energy from that food, that's a whole series of very complicated chemical reactions. Again, usually one reaction happening after another, happening after another. So I can sit here and rattle off chemical reactions all day long and tell you that's a reaction, that's a reaction. But the question is, what exactly are they? What exactly does it mean to react, or for two things to react together? That is what we're going to try to tackle and discuss today. Now, humans, since the dawn of civilization, right, ever since people could look up at the sky, they're always curious. People have always tried to figure out what all the stuff around us is really made of. And in my opinion, one of the biggest discoveries, if I had to pick one to pass it down, if we wiped out all information in the world and pass it on to rebuild civilization, would probably be that there's this thing called the periodic table of the elements. And it's about 100 elements. Now, don't send me an email here. I know there's more than 100, but most of the ones at the end are all man-made, very, very short-lived radioactive elements that don't really naturally occur in nature. So you could say that the periodic table is about 100 elements that are commonly found on Earth, and that everything around you, from the metal in a golf club, to the rubber on the tires of your car, to the water that you drink, to the steak or the skin here on my body, is all made of the same roughly 100 different things. And they're put together in different combinations. I think that is one of the biggest discoveries ever, because once you understand that, you really can go forward and start building upon it, understanding how that works to discover and invent new materials and start over. You can kind of build up civilization from that point. So before the periodic table was really written down and really understood, there were lots of theories about what makes up everything around us. Right? Earth, fire, wind, water, the four elements. I'm sure there are many other theories out there that people had, right? But now we know that everything that is made of matter comes from these roughly 100 different things. So let me give you another example that sort of blows your mind. You've all heard of water, right? Water, H2O. We drink it, we need it. It is not only kind of nice, it's essential for any of us to live. H2O. Everybody learns that that's what water is. So what that means is it's made of a hydrogen, which is an element on the periodic table, and it's also made of oxygen, which is a different element on the periodic table. And they are connected, for lack of a better word, they're really bonded together, right? And they form this larger structure called a water molecule. That's what we're drinking. But if you actually look at the hydrogen gas, it's colorless. You really can't drink hydrogen, really. It's a gas at room temperature. And if you look at oxygen, it's also a gas at room temperature. It's colorless, it floats in the air, and so on and so forth. So hydrogen and oxygen have these properties that are gases, and they kind of like don't resemble water at all. But when you combine them in a certain way and make H2O, then you get this thing called a liquid, which has properties totally different than the hydrogen or the oxygen that make it up. That's why everybody thought that everything was made of so many different things, because it was hard for us to understand that you can take just about 100 simpler things and create building blocks and have properties totally different than the fundamental atoms that make it up. So these elements on the periodic table are the fundamental building blocks of everything made of matter. You may have heard of something called alchemy a long time ago when people really wanted to make gold because gold was so valuable. And they tried to find metals that were similar to gold, usually lead because it's very heavy and it seems heavy like gold, and to try to change it from lead into gold. Now, unfortunately, nobody was successful. There was a lot of trickery, but nobody was successful doing that. Why couldn't they do it? Well, that's because gold is an element. It is a fundamental element on the periodic table. It has a certain amount of protons and neutrons in the nucleus and electrons in the cloud surrounding the nucleus. But to go from lead to gold, you can't just react it with some other element on the periodic table. You need to change the number of protons and neutrons and electrons that make up the element itself. So that's a nuclear reaction. So when you have one atom changing into another atom, now we know we can do it because we smash in particle accelerators, we can do other nuclear reactions, nuclear decay, changing from one element to another. But that's not chemistry. Chemistry does not change the identity of the individual building blocks. It just rearranges their connection like Legos to other things. So here I'm mostly focusing on what is a chemical reaction. So I really want you to think of atoms on this periodic table as little bricks, like Lego bricks. Now, when you build something with little building blocks like that, you're not really creating or destroying the blocks. All you're really doing is rearranging them into new patterns, right? You can make a tall tower, you can make a skinny fat tower, you can connect lots of different types of things together. And each creation is just blocks that are stacked differently. And chemical reactions work in exactly the same way. It's just that the elements on the periodic table don't actually change their fundamental nature. They're like the Lego building blocks. So for instance, a carbon atom in the reactant, something that reacts, is still a carbon atom in the products. If I have carbon and I burn it in oxygen, it's going to make carbon dioxide and carbon monoxide. But the same carbon atom that's in the product, that's in the molecule, is the same actual carbon atom that was present before the chemical reaction happened. We haven't changed carbon from one thing to another. All we've done is we've bonded it with something, in this case oxygen, to form the products. And when you bond and make molecules, the properties of the products can be totally different. Carbon is black, dark, like charcoal, for instance. And oxygen is a gas. When you burn it, you make another gas that's transparent. So the properties of the product can be totally different than the properties of the elements that make it up. Now, usually what's going on in a chemical reaction is you have to start talking about the concept of a bond, right? Because oxygen in our air does not exist as just oxygen atoms floating around. You've probably heard of O2 gas, like in the hospital, turn on the O2, or launching a spaceship. We're launching with an oxidizer of O2, liquid oxygen or something. Because oxygen likes to, because of the nuclear forces there attracting electrons, it likes to bond with other oxygen molecules in pairs called O2. Other gases do that in the same way. Hydrogen is H2. It's really never really existing as single atoms. If you put them together, they're going to like to bond together because of the forces on the electrons there. It likes to share those electrons there. So you have bonds in the reactants. And when you form the products like hydrogen H2 and oxygen O2, and then they form H2O. What usually has to happen is the bonds in the H2 and the O2 in the reactants have to be broken. And then they are rearranged. The Legos come and rearrange in a new pattern, and it forms a new bond in the product. So when we talk about a bond from here on, I want you to think of the bond as sort of the force that holds these elements together. Now, in reality, what's happening is that the electrons that are surrounding, I know we all think of these electrons as little balls that are like orbiting, but they're really not balls. You can use that analogy to help you visualize, but they're really waves that exist around and surrounding the atom there. So sometimes it's helpful to think of them as waves because they have a wave character, and sometimes it's helpful to think of electrons as balls because they do have a particle-like character. In a nutshell, without getting too technical, the bonds that happen and that are holding together the elements in the molecule is usually a sharing of electrons, or it can be a transfer of electrons and then an attraction between two different species. But it's helpful to think of them as basically being shared. Now, you can go a level deeper. I can tell you that and tell you that bonds are the sharing of electrons. But then you might say, well, why are they sharing? Why do they want to share? Well, atoms on the periodic table, they don't want anything. They don't have a desire, right? So when I say that oxygen wants an extra electron or extra couple electrons, it doesn't want anything. It has a very strong force to pull more electrons in. So on the right-hand side of the periodic table, most of the elements are trying to attract more electrons. And on the other side, the left-hand side of the periodic table, the electrons are not held very strong. So they can donate electrons, right? So on the left side, they're wanting to give up electrons, and on the right-hand side of the periodic table, they're trying to attract or grab onto more electrons. And then you can go a level deeper and you can say, well, why are they trying to do all that stuff? Well, that comes back to the fact that the electric forces are millions of times stronger than gravity. You heard of opposites attract, right? Positive, negative charges attract. That force of attraction is millions of times stronger than an equivalent mass of gravity trying to attract two things together through gravity. So the electric forces, attractive or repulsive, are incredibly, incredibly, incredibly strong. You just can't imagine how strong they are. So if an atom has electrons around it, and those electrons are weakly held, like on the left-hand side of the periodic table, the only reason they're like that is because the way the electrons form shells around the nucleus, the outermost electron isn't feeling very much of a force from the nucleus. And it has to do with the number of electrons that are surrounding and the force of the nucleus there when you dive in the details. On the other side of the periodic table, on the right, when I tell you that oxygen loves to grab electrons, and it does. That's why so many things react with oxygen. It's called oxidation, right? The reason that oxygen wants to pull so many electrons in is because there is a stronger force on electrons that can be felt outside the atom. And you might go a level deeper and say, well, why does it do that? Well, it does that because of the way the electrons are surrounding the oxygen atom. And an electron on the outside of that oxygen atom can feel more of the force from the nucleus, the attractive force, because of the way the electrons are arranged in shells. So it all comes down to how the electrons are arranged in shells and how much of the force electrons can feel from the nucleus. That governs if atoms want to give up electrons or if they want to suck and pull in more electrons. And that governs that the atoms want to get together and share electrons and bond. And that governs the entire subject we're talking about, which is chemistry. Sometimes it helps to say things in different ways, so I'm going to try to do that here because it's the central point. Here's where I actually think it gets so interesting in chemistry. It really is all about the electrons. Literally, chemistry is moving atoms around like those Lego blocks and changing how the electrons are shared among those Lego blocks. That's it. Electrons are the key to chemistry. Every chemical reaction that you can put your finger on is essentially a dance of the electrons, with atoms either sharing the electrons or trading and transferring the electrons, or rearranging the tiny electrons to form new bonds, which are forces that are felt, as I mentioned a minute ago. And just like water flowing downhill, these electrons naturally always want to move into arrangements with lower energy states. Now, I'm going to talk a lot as we go through this about energy states. Electrons are in a high energy state or a low energy state. If that word scares you, just shake it off. Say it 10 times and the word is not that big. You'll kind of get used to it. When I say an electron is in a high energy state or a low energy state, What I'm talking about is the potential energy. Remember, in physics and chemistry, we have different kinds of energy. The kinetic energy is when things are moving. It's like the energy of motion. But there's also potential energy, like when you stretch a rubber band. It's not moving, but you know it's pulling on you. It has the potential to do some work. And so if you let it go, it's going to move. So these electrons, they are surrounding the nucleus of the atom in energy levels, right? When you learn chemistry and you learn quantum mechanics, you solve the equations that govern atoms. What we find is that electrons cannot just be anywhere they want. They're not like planets of a solar system. They can only be in certain locations, for lack of a better word. And I am simplifying here because an electron is not a ball that's in a certain spot, but still, they exist in energy states. And those energy states exist most probably at different radii farther away from the nucleus. Generally, the farther away you go, the higher the energy level. That means the higher the potential energy the thing has. You really can think of it kind of like a mountain. I want you to picture a mountain in your head, the most beautiful mountain you can think of. You are standing on top of the mountain, right? And you have a ball, right? Maybe it's just a bowling ball, a softball, something in your hand. Now, on the ground, on the top of this mountain, is a tiny depression. I mean, a very small depression. Now, you put the ball on top of that mountain, and it's very far above the ground. So you know that that ball has a very high potential energy, because if you throw the ball off the side, it's going to go kilometers down the mountain, and it's going to pick up a lot of speed and turn it into kinetic energy. But before you throw it, if you just take that ball and put it on the ground inside that tiny depression at the top of the mountain, it has an enormous potential energy, but it's still stable. In other words, if nothing comes and kicks that marble or whatever off or blows on it with the wind or anything, if it's just motionless, it'll stay up there forever, because things can be stable even in very high energy states. But the way the universe works is, in general, systems like to go from high energy states to low potential energy states, like rolling down the mountain. If you start asking why, well, then you start getting into how the universe is constructed and the rules of the scaffolding, and that's way beyond the scope of this, and I don't know that anyone actually knows those answers, right? But suffice to say that every system, whether you're sliding down a slide at the playground or sitting on top of that mountain, you want to go from the high energy state to the low energy state. But if that is sitting on the ground in a stable position, it can sit there forever without doing anything. Now, let's say that I come up and the wind just blows it gently, just enough to get it over the lip of the edge of that mountain. It gives a little energy boost, and then suddenly gravity takes over and it begins its journey all the way to the bottom, gaining speed rapidly, turning all that potential energy into kinetic energy. It wants to go to a lower energy state. And I want you to hang on to that analogy as we talk about reactions, because it is very similar. When you have reactants before they're reacted, and I'll give you examples in just a second, the electrons are surrounding those atoms and molecules in some energy state. They're stable though, like oxygen and hydrogen. They're stable. They're not doing anything in particular until you give it a little bit of extra energy, maybe from a match, maybe from something really hot that agitates the molecules and gets them crashing into each other, and also gives the electron some energy to occasionally bounce up to a higher energy state. Occasionally, one of those things is going to crash hard enough to essentially cause a cascading chain reaction where the electrons are going to come out. The rearrangement of the Lego blocks of the atoms are going to happen into, instead of hydrogen, oxygen, maybe H2O, 2 atoms of hydrogen for every 1 atom of oxygen. And the electrons are going to fall back into lower energy positions. And I'll talk more about what that means in a minute, but the analogy of rolling down the mountain is very, very strong, because the water molecule is much more stable at a lower energy position down at the bottom of that mountain compared to the reactants, the hydrogen and oxygen beforehand. And I can take that analogy to lots and lots of reactions that I'll chat with you about today. It's all about rearranging electrons to put things in lower energy states. And I'll just say as an aside that generally reactions will not proceed unless they're going to go into some sort of lower energy state. However, they can proceed if you dump a lot of energy into them and kind of make them go uphill, for lack of a better word. There are reactions like that, and we're going to talk a little bit more about those in just a minute. Now, I mentioned it because I couldn't resist, but really I need to talk a little more detail about one of the most powerful reactions in nature, the combustion of hydrogen, the simplest element, with oxygen to form water. Literally, this is rocket fuel. If you look back to the space shuttle, the three main engines on the bottom literally burned oxygen and hydrogen, and the white cloud that comes out of the rear end of it is water vapor, right? So when the hydrogen and the oxygen gases mix, with no spark, nothing happens. You need to give it a little bit of energy, like I mentioned with the mountain, to begin the process of the chain reaction. Not a nuclear chain reaction, but an electron chain reaction to get them to begin the rearrangement into more stable bonds. And that means that the final configuration of the electrons that are in the water molecule is lower overall than the higher energy state of the electrons that were in the raw molecules to begin with. Believe me, if it wasn't like that, you wouldn't be able to go that way. It would be like trying to go up a slide. You could do it by adding energy, but it wouldn't spontaneously happen. So the electrons in hydrogen and oxygen are kind of, if you want to use an analogy, they're kind of like anxious teenagers at a dance. They're in a high energy state. They're a little nervous. They don't know what to do. But when they form water molecules, they settle into more comfortable, lower energy positions. And that is the reason why when you look on this planet, it's mostly covered with water. Water is one of the most stable molecules. We see it everywhere. We see it on the moon, we see it on Mars, we see it all over the Earth. Water is extremely stable and extremely common. And that is because of what I'm explaining to you here about it being in a lower energy state. A couple of things I want to talk about in the burning of oxygen and hydrogen. You've seen it in the space shuttle. You've probably seen demos of a little hydrogen explosion. I'm not talking about a nuclear explosion. I'm talking about a chemical reaction of hydrogen and oxygen. So it releases a lot of heat. Why does it release heat? Well, the electrons that are surrounding the original molecules go into a lower energy state. There's a difference in energy. So they literally come crashing down. What happens if I throw the rock off the mountain? Well, it tumbles down and gains a lot of speed. It begins to have a lot of kinetic energy. And so that's what's happening. The electrons are crashing into lower energy positions, and the difference in energy is going into the thermal motion of the water. So everything gets very hot. And when things get hot, electrons are jumping up and down, and when the electrons fall into their position in the lower energy state, they release photons. So when we burn oxygen or burn hydrogen with oxygen, when we combust it, the light that we see is coming from the electrons settling into their lower energy levels, and the heat that we see is coming from literally the energy difference causing agitation in the final product, which we see as heat. We're going to talk about other reactions, but before we leave the concept of water, I want to show you the friendly neighborhood water molecule. Oxygen and 2 hydrogens, so literally H2O. Now notice water is a bent molecule. That comes from the idea that there are extra electrons that you can't see in this model here that are kind of pushing them down. So water is not, you might think of it as a straight molecule, right? But it's not a straight molecule. It's bent at a very precise angle that we can calculate in chemistry classes, right? All right, so you have this guy. When I tell you that the electrons are in a lower energy state around water, what do I really mean? Yeah, I draw an analogy with mountains, and I tell you it's at the bottom of the mountain. And you can use that because I'm telling you. But what does it really mean that the electrons that are surrounding all of these atoms over here when they're bonded is somehow in a lower energy state than when everything was separated beforehand? I'm going to do my best to explain. This is oxygen. Because of the nucleus and the electrons in the shell in the shells that are around oxygen, oxygen has a very strong tendency to pull in electrons. It's just because the electric force is so strong that electrons on the outside, they see more of the nuclear charge. And you get into the details of why when you study chemistry, but it really just comes down to how the electrons are distributed around oxygen. So electrons out here see more of the positive nuclear charge in the middle. So it's pulling them in stronger. Now these hydrogens, they literally have 1 proton and 1 electron. They're the simplest atom on the entire table. So they don't hold that electron really strongly. This is just a single proton there, and there's only 1 electron there. So those electrons can be stripped away easily. But when they form a bond like this, the line here means they're being shared. There's electrons being shared in the middle here. But because oxygen is good at pulling in electrons, and becomes hydrogen, only has 1 proton, and it can't hold on to electrons so good. What really is happening is they're sharing electrons, but the electron cloud, for lack of a better word, in the middle, is pulled towards the oxygen ever so slightly more. It's more electronegative is the term you use in chemistry. But basically they're shared, but not equally. They're pulled toward the oxygen more. And these over here are shared, but not equally. They're pulled toward the oxygen a little bit more. So the electrons I'm drawing with sticks here, but really they're existing physically closer to the oxygen here, right? Now, there's a positive nucleus in every atom, including the oxygen. So if the electrons are literally pulled closer to the nucleus, then they're in a lower energy state. Just like when you go down to the bottom of the mountain, you are closer to the center of the earth. So you're in a lower energy state. Gravity wants to pull, so when it pulls you down closer, then you don't have as far that you could fall any. Let's say you went halfway down the mountain. You would have half of the potential energy, right? Because you're closer to the center. The electrons that are here being pulled closer to the oxygen, since they're already being pulled closer and they're already existing closer to the oxygen, it means that there's really not much more room for them to go crashing in. They've already fallen down the mountain, so to speak, so that they're existing a little closer to the oxygen. So that's what I mean. The H2 gas is two atoms of hydrogen, identical, and they're equally sharing electrons before the reaction. The O2 gas is two oxygen atoms equally sharing the electrons between that are bonded before the reaction, equally. That means roughly in the middle. But after the reaction, the electrons are pulled closer to the oxygen than they are to the hydrogen. And because they're pulled closer, it is almost exactly like falling down that mountain. Once you've already exhausted the fall, there's not much more that you can fall. And that's what it means to be in a lower energy position in the final molecule. And that's why reactions occur. Now I'm using this reaction, but really it applies to all reactions. And so that's what we're going to talk about here as I give you another example. So you may or may not have seen a classic chemistry demo. Probably one day I will do it myself. If you drop a piece of zinc metal right off the periodic table into hydrochloric acid, it forms a very violent chemical reaction spontaneously with no match and no flame. What happens is the zinc atoms eagerly give up their electrons, and those electrons go to the hydrogen ions in the acid. That's what an acid is. It's a substance with lots of hydrogen ions in solution. So it forms hydrogen gas, and those are the bubbles that you see violently and spontaneously in that demo. So again, it's kind of like the Legos. They're rearranging, where zinc kind of goes in and shoves its way in, it kicks the hydrogen out, literally pulls it out of its position that it was in the acid. And it forms new bonds with the chlorine. Then the hydrogens that are kind of hanging around end up bonding with each other and they form that gas and the bubble comes up there. So the electrons, again, they're cascading from a higher energy state into a lower energy state, and all of the extra energy from the cascading down is released as heat, and that makes that solution warm up as the reaction proceeds. And it's a similar story with other reactions. I haven't seen this reaction personally, but you have everyday experience with the products. If you take sodium and you literally combine it with chlorine gas, it really would be like a microscopic fireworks show if you could see it. The sodium atoms, again, they're on the left side of the table. They like to donate electrons because they're not strongly held. The chlorine atoms, which are on the right, they like to grab electrons just like the oxygen. And so if you have something trying to give up electrons and something that loves to suck in electrons, they end up transferring electron from one to the other, and then the ions are attracted together very violently, forming sodium chloride, which you have everyday experience with. That is common table salt. Now here's something cool about chemical reactions that I've talked about and I've hinted at a few times, but I want to really put a fine point on it here. The reactions are either going to release energy or absorb energy. So when reactions release energy, we call that exothermic. So that would be like the zinc in the hydrochloric acid that gets warm, or the burning of wood with oxygen in a fireplace or something like that. That's exothermic. It releases energy. The solution of the zinc and the hydrochloric acid, it gets warm because energy is being released during the chemical reaction. The breaking of bonds and the forming of bonds having an energy difference, it has to go somewhere, and it goes into heating up the products there. But some chemical reactions are closer to climbing uphill back to the top of the mountain. And they actually need energy to soak in energy from the external environment to actually happen. And those are called endothermic reactions. So exothermic, endothermic. A perfect example of that is, you know, those little cold packs for injuries. When you crack it open, you hear it, you shake it up a little bit, you're starting a chemical reaction that begins to absorb heat energy from the surroundings. And that's why it feels cold, because it's absorbing heat from your hands or whatever part of the body that it's touching. Another example would be the reaction between baking soda and vinegar, the volcano you probably made when you were in like 3rd grade or 4th grade. That is, if you're paying attention, when you actually mix it together, it gets a little chilly to the touch. That's another endothermic reaction, absorbing energy as the reaction proceeds. So I want to stress to you that almost everything you see around you, other than ice melting or freezing, or any other change that really you see on an everyday basis, it's probably a chemical reaction of some sort. Lots and lots and lots of things like to react with oxygen, right? We respirate on oxygen. We have chemical reactions in our body reacting with oxygen, putting things on the counter, changing color, metals rusting or turning, tarnishing or things like that is always a chemical reaction. But the question that I want to touch on now before we close out here is, how does a chemical reaction differ from a nuclear reaction? And I've touched on it before, but I'd like to put a fine point on it here. Everything I've talked about up to this point involves the rearranging of these electrons around an unchanged atomic nucleus. The atomic nucleus in all of these examples never changed, only of the electrons and then where the atoms were attached to, the other Lego blocks. But nuclear reactions are different. So in a nuclear reaction, the atomic nuclei themselves are changed in some sort of way. They're either split apart, fused together, or some radioactive decay happens that very slightly changes it, the nucleus, into something slightly different. And when you change the something about the nucleus, you're going to be changing from one element to the other on the periodic table. So the entire periodic table starts with hydrogen, atomic number 1. That means there's a single proton in the nucleus and a single electron going around. And I know it's not really orbiting like a planet, but that's what we have in our mind as a model. Then you go to helium. And then you have, as you go up and through the periodic table, what you're doing is you're adding protons to the nucleus. You're also adding neutrons, which don't have any charge, but they do contribute to the mass of the atom. But the character, what turns it from lithium into sodium, or what turns it from hydrogen into helium, that is only governed by the number of protons and indirectly by the number of electrons because of that, but the number of protons in the nucleus. Atomic number 1, 2, 3, 4, 5, 6, 7, they differ by the number of protons in the nucleus. That's the most important thing there, right? So if you could change the nucleus by adding a proton, you would literally change the element from something on the periodic table to its next door neighbor. That is really what nuclear reactions are. If you smash things together in a particle accelerator, you can fuse things together, like what's happening in the sun, turning hydrogen into helium, literally, by fusing them together, because helium has 2 protons and hydrogen has 1. So it's hard to fuse things together, though. You know why? Because you have electrons surrounding. And I told you, the electric forces are millions of times stronger than gravity. So if you have 2 hydrogen atoms with electrons surrounding, and you try to get them close, the electron clouds repel each other. It's hard to get them close. The only reason the sun can do it is because it's so big, gravity can suck them in and make it happen. Or a particle accelerator could maybe smash it into happening on a small scale. But it's very, very different to get them to fuse. But if you can overcome the repulsive nature of those electron clouds and get the nuclei, which also repel each other, to come together, the strong nuclear force will take over, which is another force in nature, bond them together, and then you would have helium with a totally different character than the hydrogen on the periodic table. So that is the main difference between a nuclear reaction and a chemical reaction. In a nuclear reaction, you're changing the character of the nucleus. Maybe a proton spontaneously, through a radioactive process, changes into a neutron, or which means it has 1 less proton on the periodic table. Then it's going to move 1 spot over on the periodic table. Or a neutron spontaneously, through a radioactive process, changes from a neutron into a proton. Then you're going to slide 1 direction the other way on the periodic table, because it's the number of protons that governs what the element is. That's a nuclear reaction. But in a chemical reaction, you're not touching the nucleus at all. It's not involved at all. Just the electrons surrounding can change and bond in different ways. And of course, the number of atoms can make chains and other things that make new molecules. So the next time you see a candle burning, or rust forming on a bike, or even your own body digesting food, I really want you to remember something. You're watching an intricate dance of electrons. That's really what's going on at a fundamental level. In chemistry, it really is all about the electrons moving around and atoms finding new partners, forming new bonds, releasing energy, and releasing those sweet, sweet, low energy states. Chemical reactions aren't just transforming matter, they're the choreography that keeps our universe dancing. I know that's a little bit sappy, but really it's happening all the time around us. And I really wanted to clarify what a chemical reaction is, because it's so easy to throw it out there and say, this reacts with this, and you don't really know what's going on. So I tried to give you some specific examples, go a little bit deep in some areas, hopefully not too much, hopefully hit the right level. So I'm Jason. I'm going to sign off for now. I think that's enough. Thank you so much for hanging out with me today. I really honestly would like you to drop me a line, leave me a comment, send me an email. Let me know, was this too much detail, not enough detail? Did you like it? Please let me know. I read and respond to as many comments as I can. And as you watch something as simple as a glass of water fill up in front of you and then take a drink, I want you to remember and think about the chemistry going on, and always remember to stay curious. Learn anything at mathandscience.com.